This is Food Chemistry Unit 2, Chapter 4, Basic Food Chemistry, the Nature of Matter. Chemistry is the study of the makeup, structure, and properties of substances and the changes that occur. Chemistry is necessary to understand why ingredients in food react the way they do. To understand chemistry, we need to understand matter. Matter is anything that occupies space and has mass, like food. And this is a neat video to look at. It looks at, like, is food natural or not, like how many chemicals are actually in the food. I show this in class. It'll be posted in Schoology if you'd like to take a look. So here we're going to look at the basic nature of matter. This is essentially a review of matter, which you should have seen either in physical science or chemistry. So all matter is made of atoms. That's the smallest unit of any substance. The atom itself is composed of subatomic particles or smaller particles. The center of the atom is the nucleus. The nucleus contains the protons and neutrons. Protons have a positive charge. Neutrons have no charge or are neutral. So it's right here. This is the nucleus, proton and neutron. Electrons are found in orbitals around the nucleus and have a negative charge. And electrons are much smaller than protons and neutrons. This is not the most accurate depiction of the atom, but it's pretty common if you just search it. But basically, the electrons are around the nucleus in orbitals, and it's their movement that actually determines different reactions. And this is an awesome video. It's Dogs Teaching Chemistry. It's a little review of the parts of the atom, and Dogs will teach it to you if you'd like to take a look. All right, so atoms make up elements. Each element is composed of only one type of atom. That's why they're pure. There's roughly 90 naturally occurring elements. The rest are synthetic or created in a laboratory, and they often are named after people like Einsteinium. Elements are arranged on the periodic table by their atomic number, which is the whole number. And it's the atomic number that has the number of protons in the nucleus of an atom of that element. It's the identity of the element. And again, it's based on the number of protons or the atomic number. And it was Mr. Dmitry Mendeleev who organized the table by properties. Elements were placed into groups based on properties. Groups are the vertical columns that are numbered and named. Periods are the horizontal rows that are also numbered. And then there's also a mass number, which is the mass of the protons and neutrons in the nucleus. And this is also included on the periodic table. It's the decimal number. So here if you look at lead, so Pb is the symbol, 82 is the atomic number, that's the number of protons, also the number of electrons. And then here is the mass number, which is the protons plus the neutrons. And it's a decimal because this is really an average of the different isotopes of the elements, but that's more for just chemistry, not really for food chem, but that's why it's decimal. And here's the table. So again, Mendeleev organized this table by properties. So these groups or columns have names, and the names are right here. These are the alkalis, alkaline earth. You've got your noble gases, halogens, things like that, transition metals. And they're in these groups based on properties. The horizontal rows are called periods. They also have numbers, and that's also related to electrons and things like that. The periodic table is broken by the staircase, which separates the metals from the nonmetals, and we will look at metals quite a bit in this course, especially when you're trying to cook things in metal pans. Metals are on the left of the staircase, and nonmetals are on the right of the staircase, with one exception, which is hydrogen. Hydrogen is the first element in the top left corner due to its size. Elements on the staircase have metallic and nonmetallic properties and are known as metalloids. So here's why we need metals. Metals conduct electricity and heat, right? They can be drawn into wires, they can be pounded into sheets like aluminum foil, but also copper and gold, like gold jewelry. It's usually a solid, but mercury is a liquid. Mercury used to be in thermometers. Nonmetals are poor conductors of heat and electricity. They're brittle if they're a solid, but they can also be a liquid or a gas, such as oxygen, chlorine, and carbon. So here again, the staircase is right here. It's these metalloids, which kind of have this off-greenish color, so they do make a little staircase. Elements to the left are metals. Elements to the right are nonmetals. Hydrogen, if you notice, has this green colored box because it is a nonmetal, but it is put to the left-hand side because of its size. All right, now elements can come together and undergo chemical bonding. So a chemical bond is a force holding two atoms together. You can have an ionic bond, which is a metal and non-metal that exchange electrons. That usually involves the gaining or losing of electrons that creates ions, right? Something positive or negative. Salt is a great example of an ionic bond between sodium and chlorine, and we'll talk about salt. Covalent bonds are bonds between nonmetals that share electrons, and we will look at some covalent bonding. Sugar, for example, has covalent bonds between carbon, hydrogen, and oxygen. All right, compounds and chemical formulas. So two elements combine to make a compound, which has properties unlike the original two elements. So if you look at the formation of sodium chloride or salt, there should actually be an arrow. There we go. It says chemistry, so I want it to look like a chemical reaction. So we have sodium, Na, plus chlorine, Cl, but this would actually be Cl2 because it's diatomic, but that's a little more specific. But if any of you took chemistry, you might remember that. And it would make sodium chloride. This is not balanced or anything, but what I'm trying to show you is sodium and chlorine separately have their own properties. When they combine to make sodium chloride, this is table salt, right, which you can eat. So table salt will have different properties from the sodium and chlorine that created that, or that were used to create the sodium chloride. And this is a great video that I do show. There's a crazy scientist called Lonnie. He actually makes sodium and chlorine in a weird way. He actually makes sodium chloride, just in a little weird way. The reaction is kind of neat. Yeah, you just have to watch it to understand my point. But it's neat to see how sodium chloride is actually made from the elements. So if you'd like to take a look, that will be posted. So I do show that in class. Anywho, chemical formulas are combinations of symbols of elements in a compound. This represents one molecule of a compound right here. Knowing how to read chemical formulas helps you understand products and ingredients. So subscripts are small numbers and formulas that indicate how many atoms of each element or elements are in the compound. So if you look at water, H2O, what does this formula mean? So H2 means there's two atoms of hydrogen, and the O with no number really means O1. So this is two atoms of hydrogen for every one atom of oxygen. Formulas, particularly with carbon, are written in a way that show how the elements are connected to carbon. So that's what we're going to practice right here. How many atoms are in the following? Okay, so let's figure out how many atoms are in the following formulas. So here you have NaCl, so you have to know how to read your elements, right? This is Na, let me get my pen to write. Na, right? That's sodium. You have one, because there's no number. This is not Ci. I don't think I'll ever give you Ci, so don't even try to look at it that way. This is Cl, it's chlorine. So you have one of each, 1 plus 1 equals 2. So there's two atoms in NaCl. Okay, now how about a little bit bigger formula here? This is actually acetic acid or vinegar. So let's just count, right? C has no number, so there's 1. H has 3. Another C, there's 1, 1 O, 1 O, 1 H. So you have 1 plus 3 is 4, and then 1, 2, 3, 4, plus another 4 makes 8 atoms in acetic acid. And one more. Now what happens when you have parentheses? So this is magnesium nitrate. Mg, right, has no number after it, so that's 1. But now this parentheses, here's where a little bit of algebra comes in. You have to distribute. So what that means is any number outside this parentheses will be multiplied. So what I mean is you have n, right? N has, if there's nothing here, it's a 1. So 1 times 2 means you have 2 nitrogens. Oxygen has a 3, and there's a 2 on the outside. So that's 3 times 2 is 6. And then you add these up. 1 plus 2 is 3, plus 6 is 9. And this is how you determine how many atoms are in a formula.